Welcome to Ultimate Sleep Doctor. Tonight, we'll drift into a quiet exploration. Consider the heart of a star, a radiant core generating unimaginable energy. That same principle, harnessed with incredible precision, underlies nuclear power. It's a fascinating dance of atoms, a controlled reaction yielding a potent, clean force. Scientists have spent decades studying this remarkable process, revealing its potential and understanding its complexities. There's a deep, almost meditative quality to this controlled release, a reminder of nature's own vast, silent power. It invites a sense of wonder and a peaceful acceptance of the universe's secrets. If you find these explorations soothing, please consider liking this video and subscribing to Ultimate Sleep Doctor. Together, we can soothe more wandering minds, one peaceful night at a time. Just breathe. Let your thoughts drift like clouds across a twilight sky. Let's begin. The year was 1938. The air in Berlin hung thick with a peculiar sort of excitement, a nervous energy buzzing beneath the surface of everyday life. It wasn't a joyful excitement, not quite. There was a sense of profound discovery brewing, a discovery that would ultimately reshape our understanding of the very building blocks of the universe. Two brilliant chemists, Otto Hahn and Fritz Strassmann, were meticulously working in a laboratory at the Kaiser Wilhelm Institute, and they were on the verge of stumbling upon something extraordinary, something that would change the world forever. Their task was simple, in its apparent simplicity, to investigate the behavior of uranium when bombarded with tiny particles called alpha particles. Alpha particles are essentially helium nuclei, the core component of an atom, and they're released during radioactive decay. Hahn and Strassmann were part of a larger research group, led by Walther Bothe, who were exploring the potential of using these alpha particles to study the atom itself. They were using a device called a Geiger counter, a marvelous invention that registered the flashes of radiation emitted during these experiments. Their method was straightforward. They would shine a beam of alpha particles from a radioactive source, like radium, onto a sample of uranium. The uranium atoms, being unstable, would occasionally absorb one of these alpha particles. This absorption was believed to transform the uranium atom into a lighter element. The team hypothesized that uranium, upon absorbing an alpha particle, would decay into barium, a relatively light element, and perhaps some other, as yet undetermined, element. They meticulously recorded the results, carefully measuring the intensity of the radiation emitted after each bombardment. They expected to see a clear and predictable change, a decrease in the uranium's radioactivity, coupled with the emergence of a new radioactive element. What they actually observed, however, was utterly baffling. The initial measurements were perplexing. The Geiger counter continued to register a surprisingly high level of radioactivity, far greater than what would be expected if uranium had simply decayed into barium. It was as if the uranium was becoming more radioactive, not less. Hahn and Strassmann repeated the experiment countless times, varying the energy of the alpha particles, adjusting their techniques, and meticulously checking their equipment for any possible error. Yet the results remained stubbornly consistent. They began to suspect that something fundamental was happening within the uranium atom itself, something that contradicted the established rules of chemistry and physics. They were facing a puzzle of immense complexity. They painstakingly documented every observation, every fluctuation in the radiation readings. They realized that the observed increase in radioactivity wasn't a simple decay. It was as if the uranium atom was splitting apart, dividing into two smaller atoms. This was an entirely new phenomenon, one that nobody had ever conceived of before. Hahn, a skilled chemist, focused on the chemical aspects of the process, while Strassman, a brilliant physicist, worked on the physical implications. They independently arrived at the same astonishing conclusion. The uranium nucleus was undergoing nuclear fission. Nuclear fission is a process where a heavy atomic nucleus, like that of uranium, is split into two or more smaller nuclei, releasing a tremendous amount of energy in the process. The energy released stems from the conversion of a tiny amount of mass into energy, as described by Einstein's famous equation, E equals mc2, where E is energy, m is mass, and c is the speed of light. The uranium nucleus, after absorbing an alpha particle, didn't simply transform into barium. Instead, it fractured, creating lighter elements, primarily barium and krypton, and releasing a barrage of neutrons, those tiny particles that make up the nucleus of an atom. These newly released neutrons could, in turn, strike other uranium nuclei, causing them to fission as well, creating a self-sustaining chain reaction. The implications of this discovery were immediately clear, though initially, the full extent of their significance wasn't yet understood. Hahn and Strassman presented their findings to the German Physics Society in November 1938. Their presentation was met with skepticism and, frankly, a degree of confusion. The prevailing scientific understanding at the time was that the atom was an indivisible, solid sphere. The idea of an atom splitting open was considered almost heretical. Many of the other scientists present didn't fully grasp the profound implications of what Hahn and Strassman had discovered. However, a young physicist named Leo Szilard, recognizing the immense potential of their work, immediately saw the possibility of harnessing this energy. Szilard worried about the potential for this knowledge to be used for destructive purposes, particularly by the Nazi regime who were rapidly gaining power in Germany, took it upon himself to alert the world to the danger. He collaborated with other scientists, including Albert Einstein, to write a letter to President Franklin D. Roosevelt, urging the United States to begin researching the possibility of developing an atomic weapon. Einstein, a pacifist, was motivated by the fear that Germany might be the first to unlock the power of fission. He understood that the discovery of nuclear fission could lead to a weapon of unparalleled destructive power. Hahn and Strassman, largely unaware of Szilard's efforts and the potential consequences of their discovery, continued their research at the Kaiser Wilhelm Institute. They published their findings in a series of papers in the scientific journal Naturwissenschaften in December 1938 and January 1939. These publications provided detailed evidence of the fission process, solidifying their place in the history of science. The German government, under the direction of Walter Bauer, seized the Institute's records, including Hahn's research, ostensibly to ensure it wouldn't fall into enemy hands. This action, driven by Nazi paranoia, further complicated Hahn's life and career, leading to a period of personal hardship. Despite the political turmoil, Hahn and Strassman's discovery had irrevocably altered the course of science and ultimately the world. They had stumbled upon a fundamental process of the universe, a process that would eventually lead to both incredible advancements in energy production and, tragically, to the creation of the most devastating weapon ever known. Their meticulous work, fueled by curiosity and a dedication to scientific truth, had unleashed a force that would change everything. The news from Berlin in late 1938 was a strange one, a quiet, unsettling puzzle presented by Otto Hahn and Fritz Strassmann. They had meticulously measured the results of bombarding uranium with neutrons, and their data was utterly perplexing. They observed that after the bombardment, the uranium nucleus didn't simply break apart into smaller, known elements as they initially expected. Instead, they consistently found barium, a relatively heavy element, present in the products. This was a problem, a significant one. It suggested that uranium, when struck by a neutron, was undergoing a transformation, changing its very nature. Hahn, a meticulous chemist, was understandably frustrated, calling it one of the most astonishing findings of my life. However, Hahn and Strassmann lacked the theoretical framework to truly understand what was happening. They had observed the effect, the peculiar presence of barium, but they couldn't explain why this was occurring. They published their findings in Naturwissenschaften, carefully documenting their experimental procedures and observations. But the scientific community was, understandably, bewildered. Many dismissed it as an experimental error, a mistake in their measurement techniques. The sheer strangeness of the observation, a seemingly stable element transforming into another, was too difficult to accept. Fortunately, across the Atlantic, a brilliant physicist named Otto Frisch was grappling with a similar puzzle. Frisch, a young, exceptionally gifted scientist working with Lise Meitner, had been deeply immersed in the theoretical exploration of radioactivity. He was intimately familiar with the concept of nuclear fission, a term he'd coined alongside Ernest Rutherford in 1938, primarily as a possible explanation for the energy released during radioactive decay. He recognized that the data Hahn and Strassmann were reporting fit a specific theoretical scenario. Lise Meitner, a theoretical physicist of extraordinary skill and insight, was working alongside Frisch at the Kaiser Wilhelm Institute in Berlin. Meitner, a refugee from Nazi Austria, had been forced to continue her research in Germany despite the rising tide of anti-Semitism. She possessed a profound understanding of nuclear physics, particularly concerning the structure of the atomic nucleus. She was a crucial, yet often overlooked, figure in this unfolding drama. She had been wrestling with the implications of Hahn's findings, recognizing the potential significance of this seemingly impossible transformation. Frisch, spurred by a chance conversation with Meitner, began to build a theoretical model. He realized that the energy released during the reaction was far greater than could be explained by simple nuclear decay. He suspected, with increasing conviction, that the uranium nucleus was fissioning into two smaller nuclei, and that this splitting was releasing a tremendous amount of energy. He applied the concept of mass defect, a term he'd introduced with Rutherford, to the problem. Mass defect refers to the difference between the mass of the original uranium nucleus and the combined masses of the resulting barium and krypton nuclei. He realized that this mass difference wasn't simply lost. It was converted into energy according to Einstein's famous equation, E equals mc2, where E represents energy, m represents mass, and c represents the speed of light, a truly colossal number. Frisch, with Meitner's guidance, began to model the process, outlining the steps involved in the fission of uranium. He and Meitner worked tirelessly, meticulously calculating the energy released and outlining the characteristics of the fission process. Crucially, Frisch and Meitner realized that the fission process didn't just produce barium and krypton, it also released several neutrons. This was a critical observation. These newly released neutrons could, in turn, strike other uranium nuclei, causing them to fission and release even more neutrons. This created a self-sustaining chain reaction, a concept that initially seemed frighteningly unstable. They published their joint paper in Nature on November 28, 1938, a paper that powerfully articulated their understanding of the process. The paper meticulously described the chain reaction, using a clever analogy of falling dominoes to illustrate the sequence of events. They predicted the enormous energy potential and, importantly, highlighted the dangers of uncontrolled chain reactions. The paper was immediately recognized as a brilliant solution to the puzzle presented by Hahn and Strassmann. The paper's clear and concise explanation of the chain reaction, coupled with Frisch's innovative use of the domino analogy, rapidly gained widespread acceptance within the scientific community. It provided the crucial missing piece of the puzzle, the theoretical understanding of how the reaction could proceed, and more importantly, the implications of a chain reaction. While Hahn and Strassmann had made the initial discovery of the unusual products, it was the combined brilliance of Frisch and Meitner who truly unlocked the secret of nuclear fission. Frisch provided the theoretical framework, and Meitner's deep understanding of nuclear physics and her mathematical prowess were instrumental in solidifying the concept and predicting its devastating potential. Their work established the foundation for the development of nuclear weapons and, eventually, for the harnessing of nuclear energy for peaceful purposes. It stands as a testament to the power of collaboration and the importance of diverse perspectives in scientific discovery. The chill of Chicago in December 1942 wasn't just a feeling. It was a palpable presence clinging to the air around the University of Chicago's squash court. This wasn't a space for leisurely games. It was, remarkably, the heart of a desperate race. Physicists, mathematicians, and engineers were huddled within its low-ceilinged confines, driven by a singular, audacious goal: to create a self-sustaining nuclear reaction. The story of this endeavor, ultimately culminating in the demonstration of the first controlled chain reaction, is inextricably linked to the name of Enrico Fermi. Fermi, a brilliant Italian physicist who had already earned international acclaim for his work on alpha decay, and his crucial role in developing the alpha track method for detecting radioactive particles, had been brought to the United States in 1938. His expertise in instrumentation and his remarkable ability to build complex apparatuses made him an indispensable component of the Manhattan Project, the top-secret effort to develop an atomic bomb. The urgency of the situation was overwhelming. The Germans, it was feared, were also pursuing this technology, and the Allies needed to act swiftly. The theoretical groundwork for a chain reaction had been laid by scientists like Meitner and Frisch, but translating theory into a demonstrable reality demanded a practical, hands-on approach. Fermi, with the assistance of a dedicated team including Leo Szilard and Herbert Taubman, was tasked with designing and building the apparatus that would achieve this. Their approach was methodical and utterly focused. They recognized that the key lay in carefully assembling a configuration of uranium-235, a particular isotope of uranium, sufficient to trigger and maintain a nuclear reaction. Uranium, in its natural state, wasn't inherently radioactive in the way that Meitner and Frisch had observed. It contained a mixture of isotopes, most notably uranium-238, which was stable. However, uranium-235, though present in a relatively small quantity, possessed a property crucial to their undertaking. When a single uranium-235 nucleus was struck by a neutron, it would split apart, releasing an enormous amount of energy and, crucially, more neutrons. These newly released neutrons, in turn, would strike other uranium-235 nuclei, causing further fissions and generating even more neutrons. This was the essence of the chain reaction. The team's design involved a thick block of uranium, meticulously arranged with graphite to act as a moderator. The moderator's role was to slow down the neutrons produced during fission. Slower neutrons were far more likely to be captured by uranium-235 nuclei and induce further fission. The arrangement was deceptively simple: a central cylinder of uranium surrounded by graphite, carefully insulated to prevent heat loss. Precise measurements, meticulously recorded, were vital. They weren't simply hoping it would work. They were painstakingly adjusting the quantities of uranium and graphite to optimize the conditions for a sustained reaction. The critical mass, the minimum amount of fissile material needed to sustain a chain reaction, was a subject of intense debate. Too little material, and the reaction would quickly die out. Too much, and the energy release would be uncontrolled. Fermi and his team tackled this problem with a series of carefully controlled experiments, varying the dimensions of the uranium block and the graphite surrounding it. They utilized a sophisticated electrometer, an instrument capable of measuring extremely small electric currents, to detect the tiny bursts of current generated by the fission process. On December 2, 1942, the team conducted their final experiment. They had achieved a configuration they believed was close to the critical mass. As they initiated the experiment, a precisely timed release of neutrons into the apparatus, an eerie silence descended upon the squash court. The electrometer, which had been registering only faint, sporadic signals, suddenly began to surge. The needle swung wildly, indicating a massive increase in current. A brilliant flash of light filled the room, followed by a wave of heat. The experiment had succeeded. They had achieved a self-sustaining nuclear chain reaction. It was a moment of profound significance. The signals from the electrometer confirmed that neutrons were indeed being produced at a rate sufficient to maintain the chain reaction. The team erupted in a mixture of relief, excitement, and a dawning realization of the immense power they had unleashed. This wasn't just a scientific demonstration. It was a pivotal step in the race against the Nazis. The data collected during this experiment was meticulously analyzed, confirming their successful demonstration. The readings provided the first concrete evidence that a controlled nuclear chain reaction was possible, a stunning achievement built upon the theoretical insights of Meitner and Frisch and the practical ingenuity of Enrico Fermi. The successful experiment at the squash court marked a turning point in the Manhattan Project and ultimately in the course of human history. The world would never be the same. The late summer of 1942 was a time of intense, almost frantic activity at the University of Chicago. The war was raging in Europe, and the United States was desperately seeking a way to contribute to the Allied effort. Scientists, brilliant minds previously focused on peaceful research, were being brought together under a top-secret project known as the Manhattan Project. Their mission, to harness the power of the atom, specifically to explore the possibility of creating a weapon based on nuclear fission. But a crucial component of this effort, one that would fundamentally change our understanding of energy and the universe itself, was taking shape within the football stadium of the university. It wasn't a game being played that day. It was the birth of something far more significant, the Chicago Pile 1. The idea for this experimental reactor had come from Leo Szilard, a Hungarian-American physicist. He had been grappling with the implications of Fermi's successful chain reaction, realizing that it wasn't just about creating a powerful explosion, but about controlling and understanding this previously unimaginable energy source. Szilard approached the University of Chicago, arguing that a large, carefully constructed pile of uranium could demonstrate the feasibility of sustained nuclear fission. He proposed using graphite, a remarkably strong and stable material, as a moderator, a substance that would slow down the neutrons released during fission, allowing them to cause more fission events. A team of scientists, led by Nicholas Metropolis, a brilliant chemical engineer, began the monumental task of designing and building this pile. They faced significant challenges. First, they needed a substantial quantity of uranium, which was difficult to acquire and handle due to its radioactive properties. They ultimately secured enough enriched uranium with a higher concentration of the fissile isotope U-235, through the efforts of the GE plant in Hanford, Washington. Second, they needed to ensure the chain reaction wouldn't spiral out of control, creating an uncontrolled explosion. This was paramount. The goal wasn't destruction, but rigorous scientific investigation. The construction itself was a remarkable feat of engineering, carried out with a remarkable degree of secrecy and precision. The pile wasn't built on a solid foundation. Instead, It was constructed within the depression of Stagg Field, the university's football stadium. The depression was carefully leveled, and a lattice of steel plates, hundreds of them, was meticulously assembled to support the graphite blocks. These blocks, numbering approximately 6x6, formed the core of the reactor, the place where the magic was about to happen. Each block was precisely cut to a standard size, ensuring a uniform and stable structure. The final arrangement involved filling this lattice with approximately 7,800 individual uranium-235 fuel pins, tiny cylinders containing the fissile material. These pins were meticulously arranged, creating a remarkably dense configuration. The entire structure was covered with a thick layer of concrete, approximately 4 feet thick, to shield the surrounding area from radiation. This concrete containment was crucial, both for safety and for providing an accurate measurement of the radiation emitted. On December 2, 1942, the moment of truth arrived. A group of scientists, including Fermi, Szilard, and Arthur Compton, gathered nervously in a control room overlooking the stadium. The atmosphere was thick with anticipation. The team initiated the experiment, carefully adding carefully arranged channels of beryllium, another material that facilitated neutron multiplication, to the reactor. These channels acted as triggers, concentrating neutrons and initiating the chain reaction. Initially, nothing happened. The control room was filled with a palpable tension. Then, at 9:00 a.m. sharp, a faint blue glow began to emanate from the pile. It started as a subtle shimmer, growing steadily brighter until it became a noticeable, pulsating light. A collective gasp swept through the control room. The chain reaction had begun. Instruments meticulously recorded the energy released, primarily in the form of heat. The pile was producing a sustained nuclear chain reaction, generating a measurable amount of power. While the energy output was small, just enough to heat a few water-filled tubes, it was undeniably significant. It was the first time anyone had been able to demonstrably control and sustain a nuclear chain reaction. The Chicago Pile 1 experiment wasn't just a technical achievement. It was a profound scientific breakthrough. It proved that sustained nuclear fission was possible and opened the door to the development of nuclear power, and tragically, the creation of devastating weapons. The team's work validated years of theoretical work and laid the foundation for the next stage of the Manhattan Project, accelerating the race to build the atomic bomb. The pile operated for only 28 minutes before being shut down for safety reasons. However, those 28 minutes fundamentally altered the course of scientific history, demonstrating that the power hidden within the atom could be harnessed. The legacy of Chicago Pile 1 continues to resonate today, reminding us of the brilliant minds and courageous efforts that shaped our understanding of energy and the universe. The world in the late 1930s was a place simmering with unease. The rise of Nazi Germany, the expansionist ambitions of Japan, and the looming threat of a major European conflict created a palpable sense of dread. Scientists, brilliant minds grappling with the fundamental nature of the universe, began to quietly, and with increasing urgency, consider a terrifying possibility: the potential for weapons of unimaginable destructive power. It began, largely, with a letter. In December 1938, German scientists, led by Otto Hahn and Fritz Strassmann, reported an unexpected result from bombarding uranium with neutrons. They observed that the uranium had split, releasing a significant amount of energy, a phenomenon they called nuclear fission. This wasn't simply a new chemical reaction. It implied that the very structure of the atom could be manipulated, releasing colossal energy reserves. The implications were immediately recognized by Albert Einstein, who, upon hearing of Hahn's findings, wrote a famous letter to President Franklin D. Roosevelt. Einstein, a theoretical physicist who had spent his career pondering the secrets of space and time, wasn't a chemist, but he understood the profound significance of this discovery. He warned Roosevelt that the Germans might be pursuing nuclear research and urged the United States to investigate the possibility of creating a weapon based on this new understanding of atomic energy. His letter, delivered in September 1939, just days after Germany invaded Poland, contained the chilling phrase, "A process which might furnish the prodigious energy and could be turned against us." Roosevelt, already deeply concerned about Germany's military capabilities, took the warning seriously. He established a committee, initially led by Lyman Briggs, a chemist, to investigate the possibility of developing such a weapon. This initial investigation quickly escalated, spurred by the growing fear that Germany was indeed on the verge of unlocking the secrets of atomic weaponry. The threat felt more immediate when, in 1939, Leo Szilard, a Hungarian physicist who had been working with Einstein on similar ideas, proposed the creation of a nuclear chain reaction, a self-sustaining process where neutrons released from one fission event would trigger further fission events, rapidly multiplying the energy released. This concept, combined with the growing urgency, led to the formation of the Uranium Committee, and then in 1941, the top-secret Manhattan Project. This wasn't a single laboratory or research effort. It was a vast, nationwide undertaking, encompassing universities, private companies, and government facilities across the United States. General Leslie Groves was appointed to lead the project, bringing his extensive military experience to the challenge. He was a demanding and exceptionally organized leader, crucial to managing the enormous scale of the operation. The project's primary goal was to produce enough uranium-235, the isotope of uranium most suitable for creating a chain reaction, to build an atomic bomb before the Germans could. The Manhattan Project was structured around two main approaches. One was the Huff cycle, a complex and inefficient process developed at Columbia University, designed to separate uranium-235 from uranium ore. This method was slow, yielding only small amounts of the desired isotope. The other, more promising approach was the Galloway process, utilizing a gaseous diffusion method developed at Oak Ridge National Laboratory in Tennessee. This involved forcing uranium hexafluoride gas through tiny membranes, exploiting the slight difference in the diffusion rates of uranium-235 and uranium-238. Oak Ridge became a bustling center of activity, housing thousands of workers, scientists, engineers, machinists, and laborers, all dedicated to the production of uranium. The work was intensely secretive, with security measures stringent to prevent the Germans from gaining any knowledge of the project. Meanwhile, at Los Alamos National Laboratory in New Mexico, a team of brilliant physicists led by J. Robert Oppenheimer was tasked with designing and constructing the actual atomic bomb. Oppenheimer, a theoretical physicist with a profound understanding of quantum mechanics, would later become known as the father of the atomic bomb. The team at Los Alamos faced enormous technical challenges. They needed to design a system that could rapidly assemble a sufficient quantity of uranium-235 into a supercritical mass, a mass where the chain reaction would be self-sustaining. Different designs were explored, leading to the development of two distinct bomb types: the Little Boy, a gun-type weapon utilizing uranium-235, and the Fat Man, an implosion-type weapon utilizing plutonium-239, produced at Hanford in Washington State. The choice of plutonium was driven by the increasing feasibility of producing it artificially. As the war in Europe progressed, the Manhattan Project accelerated. The threat of a Japanese invasion loomed, and the urgency to complete the bomb intensified. The decision to use the atomic bombs against Japan was, undoubtedly, one of the most controversial events in human history, and its ramifications continue to be debated to this day. The bombs were dropped on Hiroshima on August 6, 1945, and Nagasaki on August 9, 1945, resulting in unprecedented devastation and loss of life. The Manhattan Project, born out of fear and scientific curiosity, ultimately transformed the world, ushering in the nuclear age and forever changing the landscape of warfare and international relations. The story of its creation and deployment remains a testament to the power of human ingenuity, the potential for scientific discovery to both illuminate and threaten, and the immense responsibility that accompanies such profound knowledge. The immediate aftermath of Chicago Pile 1, that small, remarkably successful demonstration of sustained nuclear fission, wasn't marked by a sudden rush to build enormous, centralized power plants. Instead, a quieter, more pragmatic approach began to take hold, driven by brilliant minds grappling with the inherent challenges and potential instability of the technology. The early reactor designs, particularly those championed by figures like Ernest Lawrence and Harold Urey, moved away from the massive, centralized models envisioned initially. They were focused on creating smaller, more manageable systems, conceived with a remarkable, almost intuitive, understanding of containment and control. These early explorations led to what became known as the shipping container reactor concept, a radically simple yet incredibly thoughtful solution to the immediate dangers of nuclear materials. Lawrence, a pioneer in particle acceleration, was deeply concerned with the uncontrolled release of neutrons, those tiny, energetic particles that were the key to sustaining the chain reaction. Simply increasing the size of the reactor, as some advocated, didn't address the fundamental problem. He realized that a robust, self-contained system, drastically reducing the volume of fissile material exposed to the environment was paramount. His work centered on creating a small, shielded reactor, essentially a miniature version of Chicago Pile 1, but with far more stringent safety features built directly into its design. The core of his concept involved a graphite moderator, similar to that used in Chicago Pile 1, to slow down the neutrons and increase the efficiency of the reaction. However, the crucial difference was the construction. Lawrence's team designed a reactor built within a reinforced concrete vessel, meticulously shaped to minimize neutron leakage. This vessel wasn't just a protective shell. It was designed to be a precisely engineered shipping container, a term that would become profoundly relevant. The concrete was chosen not only for its strength, but also for its ability to absorb neutrons, further reducing the number of particles escaping the reactor core. This containment system was surrounded by a thick layer of water, which acted as both a moderator and a radiation shield. Furthermore, the entire assembly was placed on a vibration-dampening platform to minimize mechanical stress, which could potentially trigger a sudden release of energy. The dimensions of the container were carefully calculated to contain a relatively small amount of uranium fuel, enough for experimentation and basic energy production, but nowhere near the quantities required for a large-scale power plant. Yuri, simultaneously, was pursuing a related but distinct approach, primarily focused on the practical aspects of handling radioactive materials. He recognized the immense challenge of safely storing and transporting the spent fuel from nuclear reactions, a problem that wouldn't become a major concern until many years later. His investigations led to the development of specialized containers designed to passively contain radioactive waste. These weren't intended to generate electricity, but rather to provide a safe and stable environment for the decay of radioactive isotopes. Yuri's containers shared a common thread with Lawrence's concept. They were built around a robust, shielded vessel, though constructed from materials like steel and lead, rather than solely concrete. His designs incorporated features like passive cooling systems, relying on natural convection to dissipate heat, and systems for monitoring radiation levels. The beauty of these early designs lay in their inherent simplicity and reliance on fundamental physical principles. They weren't trying to solve all the challenges of nuclear energy. They were focused on containing the immediate hazards. The shipping container concept wasn't just about physical protection. It was about creating a system where the risks were minimized through careful design and rigorous testing. The small size reduced the potential for a catastrophic accident, and the layered shielding provided multiple barriers against radiation exposure. This philosophy of containment would become a cornerstone of nuclear safety for decades to come. The research from Lawrence and Yuri, along with the work of other scientists, revealed a critical understanding. The most vulnerable part of any nuclear reactor was not the fuel itself, but the pathway for uncontrolled release of neutrons and radiation. These early experiments didn't aim to generate vast amounts of power. They were primarily aimed at understanding the physics of the chain reaction, developing techniques for controlling the reaction, and critically, establishing effective methods for managing radioactive waste. They developed instrumentation and control systems that allowed for precise monitoring and adjustment of the reactor's parameters. Importantly, these small-scale reactors led to the development of crucial operational procedures. Scientists meticulously documented every step of the process, from startup to shutdown, creating detailed protocols that would later be adopted by larger reactor designs. They developed techniques for absorbing excess neutrons, preventing the chain reaction from escalating out of control. They explored different moderator materials, seeking the most effective solution for slowing down neutrons. These early investigations paved the way for the gradual evolution of nuclear technology, shifting the focus from rapid, large-scale development to a more cautious, scientifically driven approach. The shipping container concept wasn't a final solution. It was an essential stepping stone. The design's limitations, particularly its low power output, underscored the need for larger, more powerful reactors. However, the enduring legacy of these early experiments was the systematic approach to containment and control that they fostered. The realization that a robust, shielded vessel was paramount, and that careful monitoring and control were essential for safe operation, became ingrained in the nuclear community. The early shipping container reactors were a testament to the power of scientific inquiry, a quiet revolution in how humanity approached a profoundly complex and potentially dangerous technology. They established a framework for future development, a framework built on containment, control, and a deep respect for the fundamental laws of physics. The initial reactions following the fission of uranium-235, as we've seen, release a tremendous amount of energy, mostly in the form of kinetic energy possessed by the resulting fragments like krypton and barium. However, these fragments themselves are flying around at incredibly high speeds, far too fast to be useful for sustaining a chain reaction. They'd simply bounce off the uranium fuel, generating only a tiny, fleeting burst of energy. The problem, you see, is that these fast neutrons born from the fission process are incredibly energetic and unstable. They're eager to escape, and if they do, they won't collide with another uranium nucleus to cause another fission, and the reaction stops. To keep the chain reaction going, we need a way to slow these neutrons down. This is where the fascinating concept of moderation comes in. Moderation is all about reducing the speed of these energetic neutrons without absorbing them. Absorbing neutrons would simply halt the reaction. It's a delicate balance. The material used for moderation doesn't need to absorb many neutrons. It just needs to change their motion effectively. Think of it like a billiards game. If you hit the cue ball at a very high angle and with full force, it's going to bounce around wildly, scattering across the table and failing to make a controlled shot. But if you strike it more gently, at a lower speed, it's much more likely to interact with the other balls, causing a predictable and controlled collision. Neutrons are very similar. Fast neutrons are like a fast billiard ball. They're energetic and difficult to control. Slower neutrons, on the other hand, are much more likely to interact with another uranium nucleus, increasing the chance of a further fission. The key to effective moderation is choosing a material with the right characteristics. The best moderators are materials that are light and have a large number of atoms packed closely together. This is because lighter nuclei are easier to slow down. They have lower masses and therefore less momentum. Momentum is the measure of how much something is moving, and it's directly related to speed. It's also why the density of the material is so important. A denser material means more nuclei are available to interact with the neutrons. Beryllium and graphite were early favorites for this role and continue to be used in some reactor designs. But water, specifically ordinary heavy water containing deuterium, has proven to be exceptionally successful. Deuterium, you'll remember, is a form of hydrogen where the proton is replaced with a neutron. Because deuterium nuclei contain both a proton and a neutron, they can capture and release energy more effectively than regular hydrogen, offering a slightly enhanced moderation effect. Furthermore, water is readily available, relatively inexpensive, and has excellent heat transfer properties, which is extremely important for removing the heat generated by the fission process. The process of slowing down a neutron isn't a simple collision. It's actually a series of small, elastic collisions. That's a fancy way of saying the neutron bounces off the nuclei, losing a tiny bit of energy with each collision. Each time a neutron interacts with a nucleus, it loses a small amount of its kinetic energy, converting that energy into heat. The more collisions a neutron undergoes, the slower it becomes. This is why water, or any other moderator, becomes noticeably warmer as the chain reaction proceeds. Now, there's a further step involved: thermalization. Even after a neutron has been slowed down to a relatively low speed, often referred to as thermal speed, it might not be perfectly matched to the speed distribution of the neutrons already within the reactor. The initial neutrons produced by fission are a wide range of speeds, not perfectly uniform. Therefore, the moderator doesn't just slow down neutrons. It actively shapes the neutron energy distribution, bringing the majority of neutrons closer to the thermal speed, the speed most efficiently capable of causing further fission. This shaping of the neutron energy distribution is crucial for sustaining a stable chain reaction. If the neutron speeds were randomly distributed, the reaction would be extremely unstable, with frequent surges and dips in the rate of fission. By increasing the proportion of neutrons at the thermal speed, the moderator ensures a more consistent and predictable rate of fission. This control over neutron energy is one of the key factors that distinguishes a nuclear reactor from a purely uncontrolled nuclear explosion. The effectiveness of a moderator is often described using a concept called the moderation factor. This factor represents the ratio of the neutron population at the thermal speed to the total neutron population. A moderator with a high moderation factor is very efficient at slowing down neutrons and shaping their energy distribution. Different materials have different moderation factors, and the choice of moderator is a vital design consideration for any nuclear reactor. Ultimately, the precise control of neutron moderation is what allows us to harness the incredible power of nuclear fission in a safe and controlled manner. Let's delve deeper now into the heart of what makes a nuclear reactor tick, the remarkable atom of uranium. It's not just a scary symbol on a diagram. It's a tiny world with a surprisingly complex story to tell. Uranium, in its natural state, isn't a single element but rather a mixture of several uranium isotopes. You'll find uranium-238 uranium and a little bit of uranium. Uranium is the most abundant, making up roughly 99.3% of natural uranium. However, it's this other isotope, uranium, that holds the key to controlled nuclear fission and, ultimately, the energy we harness. Uranium has a specific number 235, representing the number of protons within its nucleus. Every atom, regardless of its identity, is defined by this number, the defining characteristic of its element. The number of neutrons is then determined by subtracting the number of protons from the atom's total number of nucleons, protons, and neutrons. In the case of uranium, with 92 protons, it has 143 neutrons. This arrangement, 92 protons and 143 neutrons, is inherently unstable for this particular isotope. The nucleus of uranium is remarkably strong, resisting attempts to break itself apart. But the force holding this nucleus together, the strong nuclear force, isn't always enough to overcome the natural tendency of protons to repel each other. The inherent instability of uranium arises from the large number of protons and neutrons crammed into a relatively small space. This creates a high level of nuclear tension. Now here's where neutrons come into play, playing a crucial role. A single neutron traveling at high speed can interact with a uranium-235 nucleus. When this happens, the nucleus absorbs the neutron, becoming uranium-236, an even more unstable configuration. This newly formed uranium nucleus is incredibly short-lived. It almost immediately splits apart, a process called fission. This fission isn't a clean break, though. The uranium-236 nucleus doesn't simply shatter into nothingness. Instead, it fragments into two smaller nuclei, which are typically lighter elements like barium and krypton. And importantly, it releases a significant amount of energy, primarily in the form of kinetic energy of the resulting fragments and a large number of additional neutrons, usually between 2 and 3, depending on the specific fission event. These released neutrons are absolutely critical. Each of those neutrons traveling at high speed can then in turn strike other uranium nuclei, triggering further fission events. This is a self-sustaining chain reaction. It's like a tiny, incredibly powerful domino effect. The beauty and the challenge of nuclear power lies in controlling this chain reaction. The properties of uranium are intimately linked to its nuclear structure. The nucleus's high mass contributes to the immense energy released during fission. The energy isn't just in the movement of the fragments. It's also a consequence of the conversion of a tiny amount of mass directly into energy, as described by Einstein's famous equation, E equals mc2. This conversion is far more efficient than burning fossil fuels, making nuclear power a potentially significant energy source. Uranium, also exhibits a particular sensitivity to neutron bombardment. It's not just about absorbing a single neutron. The probability of absorbing a neutron increases dramatically with the intensity of the neutron flux, the number of neutrons per unit area. This means that even a small increase in neutron density can lead to an exponential increase in the rate of fission, potentially causing a runaway reaction. That's why careful control mechanisms are essential in a nuclear reactor. The chemical behavior of uranium is, unsurprisingly, quite similar to that of other uranium isotopes. It readily forms compounds like uranium hexafluoride, UF6, which is a gas at room temperature and is frequently used in the enrichment process. However, it's the nuclear properties, specifically its ability to undergo fission when struck by a neutron, that are paramount. It doesn't readily react with oxygen or other elements in a conventional chemical sense. Its power resides within its nucleus. Furthermore, the cross-section of uranium, a measure of its probability of interacting with a neutron, is a key factor in determining the efficiency of a nuclear reaction. A larger cross-section means a greater chance of interaction, and therefore a faster, more efficient chain reaction. Scientists carefully control the reactor's design to optimize this interaction. The enrichment of natural uranium, meaning the process of increasing the proportion of uranium relative to uranium-238, is a complex undertaking. It typically involves exploiting the slight differences in physical properties between the two isotopes, often using techniques like gaseous diffusion or gas centrifuge separation. These processes are meticulously designed to gradually shift the balance, concentrating the more desirable uranium for use in a reactor. Finally, understanding the decay chain of uranium, its eventual transformation into other radioactive elements over time, is crucial for managing spent nuclear fuel. The products of fission, including uranium, are themselves radioactive and require careful storage and disposal. It's a multi-layered story, this tiny atom's journey, from its unstable beginning to its potential for generating power. The heart of a nuclear reactor isn't simply the uranium fuel itself, although that's undeniably crucial. It's a carefully orchestrated dance, a delicate balance of energy release, and the reactor's design is specifically engineered to manage this process. The goal isn't to unleash all the energy from the uranium at once. It's to create a sustained, controlled chain reaction, providing a steady stream of heat. This control is achieved through two primary systems: the control rods and the moderator. Let's begin with the control rods. These aren't made of metal in the traditional sense, though they are largely constructed of materials like boron, hafnium, or cadmium. These materials possess a remarkable property. They are exceptionally good at absorbing neutrons. Neutrons are the tiny particles responsible for driving the nuclear chain reaction. When a uranium nucleus splits, a process called fission, it releases a tremendous amount of energy, and crucially, it releases several neutrons. These neutrons then go on to strike other uranium nuclei, causing them to split too, and so on. Without control, this process would escalate exponentially, leading to a runaway reaction and a potentially catastrophic release of energy. The control rods are inserted into the reactor core, strategically positioned to intercept these newly released neutrons. When the operator wants to slow down or even stop the reaction, they simply push the control rods further into the core. As the rods move deeper, they capture more and more neutrons, effectively reducing the number available to cause further fission. This directly decreases the rate at which the chain reaction proceeds. Conversely, to increase the reaction rate, the control rods are withdrawn slightly. Less neutron absorption means more neutrons are available to trigger further fission events, and the reactor's power output rises. The speed at which the rods are moved is incredibly precise, often controlled by sophisticated computer systems, and the amount of neutron absorption is continuously monitored. Now, let's shift our attention to the moderator. The moderator's role is intrinsically linked to the control rods, but it operates on a slightly different principle. The neutrons released during fission aren't traveling at their maximum energy when they collide with other uranium nuclei. They've been given a significant kick of kinetic energy. To increase the probability of a successful collision, that is, to ensure a neutron is absorbed and triggers another fission, the moderator is introduced. The moderator's job is to slow down these fast neutrons. It does this through a process called scattering. Imagine throwing a small pebble at a fast-moving ball. The ball will change direction, slowing down as it interacts with the pebble. Similarly, the moderator, typically made of materials like heavy water, deuterium oxide, light water, ordinary water, or graphite, acts as a collection of tiny obstacles for the fast neutrons. Each time a neutron strikes a molecule of the moderator, it loses some of its energy through collisions. The key here is that slower neutrons are far more likely to be captured by the uranium nucleus. It's like a dimmer switch. The dimmer switch controls the intensity of the light, and in this case, the moderator and the control rods together control the intensity of the nuclear reaction. The moderator doesn't directly absorb neutrons, but it dramatically increases the efficiency of neutron capture. Without a moderator, a substantial portion of the neutrons would simply speed past the uranium nuclei, never contributing to the chain reaction. The choice of moderator material isn't arbitrary. Each material has slightly different properties that affect its ability to slow down neutrons. Heavy water, for instance, is particularly effective because the hydrogen atoms in deuterium are heavier than ordinary hydrogen, leading to more forceful collisions and greater neutron slowing. Graphite, a form of carbon, is another commonly used moderator, offering a good balance of properties. The control rods and the moderator work in perfect synergy. The control rods actively absorb neutrons to limit the reaction rate, while the moderator enhances the likelihood of neutron capture by slowing them down. Reactor operators constantly monitor the neutron flux, the rate at which neutrons are moving through the core, and adjust the position of the control rods and the flow of coolant, often water, through the core to maintain a stable, desired power output. Furthermore, the design of the reactor core itself is meticulously planned. The arrangement of the fuel rods and the moderator material is carefully calculated to ensure uniform neutron distribution and efficient heat transfer. This complex interplay between the control rods, the moderator, and the core design is what makes a nuclear reactor a controlled and reliable source of energy. It's a beautiful demonstration of physics in action, a testament to human ingenuity and a careful balancing act of forces. The ongoing operation of a nuclear reactor is a continuous process of adjustment and monitoring. Sensors throughout the core detect neutron flux, temperature, and pressure, feeding this data back to the control systems. The computer system then makes tiny, almost imperceptible adjustments to the control rods and the coolant flow, maintaining the reactor in a state of stable, controlled power generation. It's a remarkably precise and sophisticated system, and understanding its core components, the control rods and the moderator, provides a fundamental insight into the workings of this powerful technology. The journey of a nuclear power plant's fuel doesn't begin with gleaming reactor cores. It starts with the Earth, with carefully extracting a remarkably complex and surprisingly costly resource: uranium. Uranium itself isn't particularly rare, scattered throughout the Earth's crust, but its usable forms, particularly the isotope uranium-235, are what make it so valuable. The process of turning that scattered material into something a reactor can use is a lengthy and intricate one, and the economics of it drive a significant portion of the overall cost of nuclear energy. Initially, almost all uranium ore is found in a relatively small number of countries. Australia, Canada, Kazakhstan, Russia, Namibia, and Niger are consistently the largest producers. These nations possess the geological conditions, specific rock formations, often associated with igneous and metamorphic processes, that concentrate uranium. The uranium ore itself varies dramatically in grade, which simply means the percentage of uranium it contains. A high-grade ore might contain 0.5% uranium, while a lower-grade ore might only have 0.05%. Economically, the higher the grade, the more efficient and less expensive the entire process becomes. Mining operations, often located in harsh environments, from the arid plains of Kazakhstan to the remote and rugged terrain of Canada, face significant challenges. Open-pit mining is common for higher-grade deposits, but underground mining is required for leaner ores, adding considerable complexity and cost. The extraction itself involves drilling, blasting, and hauling, demanding substantial equipment, skilled labor, and meticulous safety protocols. Following the initial mining, the uranium ore undergoes a process called milling. This isn't simply crushing the rock. It involves a sophisticated series of steps to liberate the uranium from the surrounding minerals. The ore is crushed and ground into a fine powder, then treated with chemicals, typically sulfuric acid, to dissolve the uranium. This creates a uranium-rich slurry called pregnant liquor. The uranium isn't entirely dissolved, however. It's mixed with a great deal of unwanted material called tailings. Tailings represent a significant waste stream, and their safe disposal is a major environmental and economic consideration. The volume of tailings produced is enormous, rivaling the size of the original ore deposit. The pregnant liquor, then needs to be processed further to concentrate the uranium-235. This is where the conversion process comes in. Uranium-238, which makes up the vast majority of naturally occurring uranium, is much more abundant than uranium-235. Reactors require a fuel enriched to increase the proportion of the fissile isotope. The conversion process, often called hexafluoride conversion, transforms the uranium into uranium hexafluoride gas. Because uranium-235 is slightly lighter than uranium-238, the gaseous mixture separates, with the uranium-235 rising to the top of the column and the uranium-238 sinking to the bottom. This isn't perfect separation. It's a partial enrichment, creating a stream of uranium that's still mostly uranium-238, but with a slightly higher percentage of uranium-235. The enriched uranium hexafluoride is then fed into a gaseous diffusion or centrifuge enrichment plant. These plants use sophisticated technologies to further increase the concentration of uranium-235. Gaseous diffusion relies on the slight difference in mass between the isotopes, while centrifuges spin the gas at incredibly high speeds, exploiting the same principle. Both methods are energy-intensive, representing a substantial portion of the overall cost of producing reactor fuel. The enriched uranium is then fabricated into ceramic pellets, which are stacked into fuel rods and ultimately assembled into fuel assemblies for the reactor. The economics of uranium mining and processing are constantly shifting due to several factors. Fluctuations in uranium prices, driven by supply and demand, directly impact the cost of producing enriched fuel. Changes in geopolitical stability, particularly in uranium-producing countries, can also cause volatility. Furthermore, technological advancements, such as more efficient conversion technologies or new enrichment methods, can significantly alter the cost structure. The development of advanced reactor designs, like fast reactors, which can consume existing spent nuclear fuel, could potentially reduce the demand for enriched uranium and reshape the economics. It's important to understand that the cost of uranium doesn't just represent the price of the raw material. It encompasses the entire supply chain, from exploration and mining to conversion, enrichment, and fabrication. This integrated cost, often representing 30–40% of the total cost of nuclear electricity, is a key consideration in the overall competitiveness of nuclear energy compared to other sources. Furthermore, uranium mining isn't a static operation. Mining operations eventually deplete a deposit, requiring the relocation to new sites, adding to the overall costs. Looking ahead, research into alternative uranium extraction methods, such as in situ leaching, where chemicals are injected into the ground to dissolve the uranium, could potentially reduce some of these costs. However, these methods also come with their own environmental challenges, requiring careful monitoring and management. Ultimately, the economics of uranium mining and processing are intrinsically linked to the broader nuclear industry, to the demand for electricity, the regulatory environment, and the ongoing innovation within the field. It's a complex and evolving picture, constantly influenced by scientific advancements and global energy trends. The dream of harnessing the incredible energy locked within the atom began with a fervent desire to provide clean, abundant power. Early nuclear reactors, conceived in the aftermath of World War II, represented a monumental technological leap. Designs, largely based on the pressurized water reactor (PWR) model, seemed robust and fundamentally sound, built on principles of heat generation and controlled cooling. However, a series of devastating events in the late 20th century revealed a crucial and unsettling truth. Inherent vulnerabilities existed within these designs, vulnerabilities that, when combined with human error and inadequate oversight, could lead to catastrophic consequences. The stories of Chernobyl and 3 Mile Island serve as poignant reminders of this stark reality, offering invaluable lessons etched in tragedy. The Chernobyl disaster, occurring in April 1986 at the RBMK-1000 reactor in Ukraine, dramatically illustrated the dangers of a specific reactor design. The RBMK reactor possessed a unique graphite moderator, which was used to slow down the neutrons needed to sustain a nuclear chain reaction. This design, while efficient, introduced a significant instability. During a safety test aimed at simulating a power failure, operators attempted to rapidly lower the reactor's power level. Due to the graphite moderator's properties, reducing power wasn't as straightforward as it appeared. Instead of a controlled decrease, the reactor rapidly accelerated, generating an enormous amount of heat. The emergency shutdown systems, designed to prevent overheating, didn't function as intended, further exacerbating the situation. The lack of a negative temperature coefficient, a crucial safety feature where a rise in temperature automatically reduces the reaction rate, meant that the reactor spiraled out of control. This led to a steam explosion, breaching the reactor's containment building and releasing massive amounts of radioactive material into the atmosphere. The immediate consequences were devastating, causing dozens of deaths and forcing hundreds of thousands of people to evacuate their homes. Beyond the immediate fatalities, the long-term health effects, including increased cancer rates, continue to be a concern. The Chernobyl disaster wasn't simply a technical malfunction. It highlighted the critical importance of robust safety culture, rigorous testing, and a deep understanding of reactor physics. It underscored the potential for runaway reactions when design parameters weren't fully accounted for in all operating conditions. Several years later, in March 1979, the 3 Mile Island (TMI) nuclear power plant in Pennsylvania experienced a near disaster. During a late-night shutdown, a loss of coolant occurred due to a combination of equipment failures and operator errors. The Emergency Core Cooling System (ECCS), designed to inject water into the reactor vessel to prevent overheating, failed to activate fully. Without adequate cooling, the reactor's fuel rods began to overheat. While the reactor automatically shut down, the event revealed serious deficiencies in TMI's design and operation. The Emergency Core Cooling System, intended to mitigate a loss of coolant accident, was found to have been improperly maintained and lacked sufficient capacity. The incident, though less dramatic than Chernobyl, prompted a thorough review of reactor safety standards across the United States. The investigation revealed that operators had made several critical errors, including failing to properly monitor the reactor's condition and failing to respond effectively to the unfolding crisis. The event exposed weaknesses in the training and procedural controls in place at the plant. It demonstrated that even a seemingly minor equipment malfunction, coupled with human error, could trigger a cascade of events leading to a potentially serious situation. The public outcry following TMI significantly increased scrutiny of the nuclear industry and spurred significant investment in reactor safety improvements. Both Chernobyl and 3 Mile Island shared a common thread: a reliance on complex systems that, when disrupted, could quickly spiral out of control. They revealed that nuclear reactor design, while possessing immense potential for energy generation, required constant vigilance, flawless execution, and a deeply ingrained safety culture. The lessons learned from these events fundamentally reshaped the nuclear industry, leading to enhanced design standards, improved operator training, and a greater emphasis on redundancy and fail-safe systems. Modern reactor designs incorporate numerous safeguards, including redundant cooling systems, automated shutdown mechanisms, and sophisticated monitoring systems. The pursuit of inherent safety, designs that intrinsically prevent accidents, became a central focus. Ultimately, the stories of Chernobyl and 3 Mile Island aren't just tales of disaster. They are powerful reminders of the responsibility that comes with harnessing such immense power and the enduring need for meticulous care and unwavering commitment to safety. The story of nuclear power truly took a significant turn in the mid-1950s, spurred by a desire for a reactor design that was both powerful and, crucially, inherently safer than those being developed earlier. The immediate aftermath of the Soviet Union's first atomic bomb test and the anxieties surrounding reactor instability fueled intense research into new approaches. This led to the emergence of the pressurized water reactor, or PWR, a design that would eventually become the dominant form of nuclear power generation globally for over half a century. The foundational concept revolved around utilizing water as both the coolant and the nuclear reaction medium. The genius of the PWR's design lay in its ingenious layering of components. At the heart of the reactor vessel was the fuel assembly. These were carefully arranged blocks, typically containing enriched uranium dioxide pellets, densely packed and precisely positioned. This arrangement maximized the surface area exposed to the intense heat generated by nuclear fission. Surrounding the fuel assembly was the moderator. In the case of the PWR, this was ordinary, light water. The moderator's function wasn't to slow down the neutrons as much as in graphite-moderated reactors. Instead, it served primarily to absorb excess neutrons, helping to regulate the reaction rate and ensuring a steady, controlled output of energy. However, the most critical aspect of the PWR design was the pressure vessel itself. This enormous, robust steel cylinder housed the entire reactor core, including the fuel assemblies and moderator. The key innovation here was the presence of a high-pressure system, Water within the reactor was maintained at an incredibly high pressure, around 150 atmospheres, or 2,200 pounds per square inch. This high pressure was absolutely vital for the reactor's operation. Because the water was under such immense pressure, it could exist in its supercritical state, a state where it possessed significantly more energy than ordinary water at the same temperature. This meant the water could transfer heat far more efficiently, enabling the reactor to generate a substantial amount of electricity. The heat generated by the fission reaction was channeled through a primary coolant loop, circulating continuously through the reactor core, absorbing the immense thermal energy. This hot, pressurized water then flowed into a steam generator. The steam generator was essentially a large heat exchanger. It was surrounded by a secondary water loop. As the hot primary water passed through the heat exchanger walls, it transferred its heat to the secondary water. This heated secondary water then boiled, creating steam, the same steam that would eventually turn a turbine to generate electricity, just as in a traditional fossil fuel power plant. The beauty of this design was its inherent stability. The high pressure acted as a natural barrier against coolant leaks. Even if there were cracks or leaks within the primary loop, the intense pressure would force the water back into the reactor, preventing it from rapidly losing heat and potentially leading to a runaway reaction. Furthermore, the reactor's control system carefully monitored the neutron flux, the rate at which neutrons were being produced, and automatically adjusted the reactivity by controlling the amount of boron dissolved in the primary coolant. Boron is a highly effective neutron absorber, and adding or removing it from the water allowed operators to precisely fine-tune the reactor's power output. The design also incorporated a negative temperature coefficient of reactivity. This meant that as the temperature of the water in the reactor rose, the reaction rate naturally decreased, providing a self-regulating mechanism. This inherent stability was a major factor in the PWR's widespread adoption and its resilience against various operational challenges. Early PWR designs, such as those at Shippingport in Pennsylvania, the first full-scale commercial PWR, demonstrated the viability of this approach. These early reactors operated reliably for decades, providing valuable operational data and contributing to the refinement of the design. Modifications and improvements were continually made, including the addition of safety features like emergency core cooling systems, designed to inject water directly into the reactor vessel in the event of a severe overheating scenario. The PWR's success wasn't just about its inherent stability. It was also tied to the advancements in materials science and engineering that accompanied its development. The steel alloys used in the pressure vessel were rigorously tested and optimized to withstand the extreme pressures and temperatures. Similarly, the design benefited from decades of accumulated experience and continuous monitoring, allowing engineers to anticipate and mitigate potential problems. By the late 20th century, PWR technology had become incredibly sophisticated. Modern PWRs incorporate advanced control systems, enhanced safety features, and improved fuel designs, demonstrating the ongoing evolution of this foundational nuclear reactor design. It stands as a testament to the power of careful design, rigorous testing, and a commitment to operational excellence within the complex world of nuclear power generation. The early days of nuclear power, after the initial successes of the EBRI reactor, highlighted a crucial point: the need for simpler, more reliable designs. The pressurized water reactor, or PWR, emerged as the dominant approach, offering a degree of safety through the constant pressurization of its coolant water. This pressure prevented the water from boiling, even at the incredibly high temperatures needed to sustain the nuclear chain reaction. The system was meticulously engineered, with redundant safety features like containment structures designed to withstand significant external events. However, the PWR's complexity presented a challenge. Maintaining that precise pressure, managing the temperature gradients within the reactor core, and handling the steam produced at the end of the process proved to be demanding operations, requiring highly skilled personnel and sophisticated monitoring systems. There were concerns about potential instabilities arising from these conditions, and the sheer number of components involved increased the possibility of equipment failure. Simultaneously, a different approach was taking shape in Japan. Researchers at Toshiba, with the assistance of scientists from MIT, were developing a fundamentally different reactor design, the boiling water reactor, or BWR. Instead of relying on external pressurization, the BWR intentionally allowed the water circulating through the reactor core to boil. This wasn't a deliberate design flaw, but rather a core principle. The steam produced directly from the boiling water was then used to spin a turbine, generating electricity, just like in a traditional steam power plant. The key difference was the source of that steam. The operational philosophy of a BWR is markedly different from that of a PWR. In a PWR, the water remains liquid throughout the entire process, flowing through a closed loop. Any steam generated is routed to a separate condenser, where it's converted back into liquid water to complete the cycle. The BWR, however, is a once-through system. The water flows through the reactor core, boils, and the resulting steam is used directly to drive the turbine. This simplified the system dramatically, removing the need for a separate condenser and associated plumbing. A critical consequence of this design is the presence of dissolved gases within the reactor coolant. Because the water is allowed to boil, it inevitably absorbs small amounts of gases, primarily moisture and heavier gases like nitrogen and carbon dioxide. These dissolved gases have a significant impact on the reactor's behavior. They affect the neutron moderation characteristics of the water, influencing the rate at which the nuclear chain reaction proceeds. This is known as void fraction, the volume of steam bubbles present in the core. The BWR's response to void fraction is a fascinating example of feedback control. As the void fraction increases, the neutron moderation decreases, slowing down the chain reaction. The reactor automatically responds to this reduction in neutron flux by increasing the power output, attempting to compensate and maintain the desired level of heat generation. Conversely, if the void fraction decreases, the reactor reduces its power to prevent a runaway increase. This inherent feedback mechanism, while requiring precise monitoring, offered a level of stability and robustness that was somewhat lacking in the rigidly controlled environment of the PWR. Furthermore, BWRs operate at slightly lower pressures than PWRs, typically around 75 to 80 bar, approximately 1060 to 1160 psi. While this might seem inconsequential, it translates into a lower overall system pressure and reduces the potential for catastrophic failure in the event of a component rupture. The simpler design also meant fewer moving parts, reducing the potential for mechanical problems. The first commercial BWR, the Mahama BWR, began operation in Japan in 1977. The design quickly gained traction, particularly in countries seeking a more straightforward and readily understood nuclear power technology. It was seen as a more intuitive system, reducing the reliance on highly specialized expertise. However, the BWR's operation demanded a deep understanding of the influence of void fraction on the reactor's dynamics. It wasn't simply a matter of controlling temperature and pressure. It required careful management of the ever-changing environment within the reactor core. Despite its advantages, the BWR faced some specific challenges. The dissolved gases presented a constant source of uncertainty, requiring sophisticated modeling and control strategies. The potential for streamline instabilities, rapid fluctuations in void fraction needed careful attention. The reactor operators had to continuously monitor and adjust the system to maintain stable operation. Yet, the BWR proved to be a reliable and effective source of electricity, demonstrating that a fundamentally different approach to nuclear reactor design could be just as successful. The evolution of reactor design continues, incorporating lessons learned from both PWRs and BWRs, and pushing the boundaries of nuclear technology. However, the rise of the boiling water reactor marked a significant shift in the thinking about nuclear power, showcasing the value of a more direct and adaptable design, one that embraced the inherent dynamics of the nuclear reaction itself. The heart of any nuclear power plant, the engine that creates the energy, resides within the carefully crafted fuel rods. These aren't simply fuel sticks. They're incredibly complex structures designed to precisely control the incredibly powerful reaction taking place within the reactor core. Think of them as tiny, self-contained worlds of nuclear potential, meticulously managed to ensure a steady and safe output of electricity. Each fuel rod is made of a zirconium alloy, a remarkably strong and corrosion-resistant metal chosen specifically for its ability to withstand the extreme temperatures and radiation generated during nuclear fission. This alloy forms the outer shell, protecting the fuel itself. Within this protective shell are uranium-235 atoms, the special ingredient that allows the nuclear reaction to proceed. Uranium is a rare isotope, meaning it's a specific version of uranium with a particular number of neutrons. It's this isotope's characteristic, its willingness to split apart, that provides the energy for the entire process. The uranium is not in a solid block. Instead, it's fabricated into small ceramic pellets, each roughly the size of a pencil eraser. These pellets are incredibly dense, packed with uranium-235, and they're arranged in a cylindrical shape. These cylindrical shapes are then stacked together, along with the zirconium alloy cladding, to create a single fuel rod. Now consider the process of fission itself. When a uranium-235 atom is struck by a neutron, it rapidly splits apart, releasing a tremendous amount of energy in the form of heat and, crucially, more neutrons. These newly released neutrons then go on to strike other uranium-235 atoms, triggering further fission events, a chain reaction. The rate of this chain reaction is absolutely critical. If it's too fast, the reactor core could overheat and become dangerously unstable. If it's too slow, the plant wouldn't produce enough energy. That's where control rods enter the picture. These rods are made of materials like boron or cadmium, substances that readily absorb neutrons. They're inserted into the reactor core, and by adjusting their position, operators can precisely control the number of neutrons available to cause further fission. Pushing the control rods further into the core absorbs more neutrons, slowing down the chain reaction. Pulling them out allows more neutrons to be available, speeding up the reaction. It's like a dimmer switch for nuclear energy, offering a very fine level of control. The level of neutron absorption is constantly monitored and adjusted to maintain a stable and efficient power output. The fuel rods themselves aren't static. They steadily consume uranium-235, becoming depleted as the chain reaction continues. As the uranium is used up, the rods become less efficient, and the reactor needs to be shut down for a period of time to allow for replacement. This leads us to the concept of the fuel cycle. The fuel cycle encompasses everything that happens to the nuclear fuel, from its mining to its eventual disposal. First, the uranium fuel needs to be mined, typically from open-pit mines or underground facilities. The ore is processed to extract the uranium, and then the uranium is converted into uranium dioxide, a powder that's then pressed into the ceramic pellets we've already discussed. These pellets are then assembled into fuel rods, and these rods are bundled together into fuel assemblies, larger units that are placed inside the reactor core. These assemblies are designed to withstand the intense heat and radiation. Once a fuel assembly reaches the end of its operational life, it's removed from the reactor. This spent fuel is extremely radioactive and requires careful handling and storage. Initially, spent fuel assemblies are stored on-site at the nuclear power plant. However, due to their high radioactivity, this is a temporary solution. A long-term solution involves reprocessing the spent fuel. Reprocessing involves separating out the usable uranium and plutonium from the spent fuel. The separated uranium can be converted back into fuel rods, and the plutonium can be used as fuel in other reactors. However, reprocessing is a complex and controversial process, generating radioactive waste products that still need to be safely managed. Alternatively, the spent fuel can be vitrified, meaning it's encased in a glass-like material to contain the radioactive elements. This vitrified waste is then buried deep underground in a secure geological repository. The goal is to isolate the waste from the environment for thousands of years, allowing the radioactivity to gradually decrease. The management of the nuclear fuel cycle is therefore a multifaceted undertaking, requiring careful planning, advanced technology, and stringent safety protocols. It's a delicate balancing act between harnessing the immense power of nuclear fission and mitigating the risks associated with its waste products. Ensuring the safety and responsible management of nuclear fuel is paramount to the continued viability and acceptance of nuclear power as a source of clean energy. The heart of any nuclear power plant, after the careful management of its fuel and the sophisticated engineering of its containment structure, lies in the clever and continuous process of generating electricity. It all begins with a phenomenon that's been observed and harnessed for millennia: nuclear fission. Inside the reactor core, specifically within the fuel rods, a carefully controlled chain reaction unfolds. These fuel rods, typically made of uranium enriched to a specific concentration, contain tiny atoms of uranium-235. Uranium is a special kind of atom. It's fissile, meaning it's readily split when struck by a neutron. When a slow-moving neutron collides with a uranium-235 atom, something incredible happens. The uranium atom doesn't just disappear. It breaks apart, splitting into smaller atoms, primarily barium and krypton, along with releasing a tremendous amount of energy and, crucially, more neutrons. This initial splitting is the starting point of the chain reaction. These newly released neutrons then go on to strike other uranium-235 atoms, causing them to split in turn, and so on. It's like a ripple effect, a very energetic and precisely regulated ripple. This splitting process is the source of the vast majority of the heat generated within the reactor. Each fission event produces a measurable amount of thermal energy, heat. Now, this isn't the kind of heat you get from a campfire. It's a far more concentrated and powerful energy release. Because of the sheer number of uranium atoms in the core and the constant, controlled splitting, the reactor core steadily builds up a significant amount of heat. The design of the reactor core, including the arrangement of the fuel rods and the presence of control rods, is vital in ensuring that this heat generation remains consistent and predictable. To transform this intense heat into something useful, that is, usable energy, engineers use a system of water. This water circulates continuously through the reactor core. It's not just any water. It's specially treated to withstand the incredibly high temperatures and pressures within the reactor. This water absorbs the heat generated by the nuclear fission process, becoming incredibly hot. The temperature of the water as it leaves the reactor core can reach well over 300 degrees Celsius. That's hotter than a typical oven. This superheated water then flows into a component called a steam generator. The steam generator is essentially a large, complex heat exchanger. It's designed to transfer the heat from the extremely hot water from the reactor core to a separate water loop. Importantly, the water circulating within the reactor core and the water flowing through the steam generator remain completely separate. This separation is crucial for safety. It prevents any radioactive contamination from the reactor core from entering the turbine hall, where the electricity generating equipment is located. Inside the steam generator, the hot water from the reactor core flows past tubes containing a second loop of water. Because of the temperature difference, the extremely hot water flowing past the cooler water in the second loop, the cooler water rapidly turns to steam. This is a classic example of thermodynamics in action. Heat energy is transferred from one substance to another, causing a phase change. The steam produced is essentially pure water vapor, and it's produced at a very high pressure. This high pressure is key to the next stage in the process. The steam generated in the steam generator is then directed towards a turbine. A turbine is essentially a large fan, but instead of being powered by air, it's powered by steam. As the high-pressure steam rushes through the turbine blades, it causes the turbine to spin rapidly. This spinning turbine is directly connected to a generator. The generator, with its rotating coils of wire within a magnetic field, converts the mechanical energy of the spinning turbine into electrical energy. It's a remarkably efficient process. A large proportion of the energy initially released through nuclear fission is ultimately converted into electricity. Once the steam has passed through the turbine, it's cooled and condensed back into water. This cooling is accomplished using a condenser, which utilizes a large body of water, often from a nearby river or lake. The cooled water is then pumped back into the steam generator, completing the cycle and preparing it to be heated once again by the reactor core. This continuous loop, heat generation, steam production, turbine rotation, and electricity generation, is what keeps a nuclear power plant running, providing a steady and reliable source of electricity. The design and precision of each component within this system are what allow for safe and effective power production. The heart of a nuclear power plant's operation and the source of its immense energy is fundamentally linked to a process called radioactive decay. It's a natural tendency within certain atoms to become more stable, a sort of internal restlessness that manifests as the release of energy and particles. This isn't a violent explosion, it's a gradual transformation, happening constantly at the atomic level. Understanding the specifics of this decay is key to appreciating how nuclear power plants work safely and efficiently. There are several different ways this decay can occur, each resulting in a different type of radiation. The first we'll explore is alpha decay. Certain heavy atoms, particularly those in the middle of the periodic table like uranium and thorium, are prone to alpha decay. These atoms possess a large nucleus packed with protons and neutrons. This creates a situation of inherent instability. To reduce this instability, the nucleus will eject an alpha particle. An alpha particle isn't a tiny, dangerous bullet, as it's often portrayed. It's actually a helium nucleus, 2 protons and 2 neutrons bundled together. Because it's so heavy, it loses almost all of its energy as it travels, typically only penetrating a few centimeters of material. More importantly, because it's composed of positively charged particles, it's easily stopped by a sheet of paper or even a few centimeters of air. The emission of an alpha particle causes the nucleus to shrink, becoming a smaller, lighter atom, often belonging to a different element entirely. For example, when uranium-238 undergoes alpha decay, it transforms into thorium-234. Next, we have beta decay. This occurs in atoms with an excess of neutrons. Instead of ejecting a particle, the nucleus emits a beta particle, which is actually an electron. The electron is created from a neutron within the nucleus. This transformation is governed by a process called beta-minus decay, where a neutron converts into a proton, an electron, and an antineutrino. The electron, being negatively charged, is then emitted from the nucleus. Beta particles are more penetrating than alpha particles, capable of passing through a few millimeters of aluminum. They're still relatively easily shielded, however. The emission of a beta particle reduces the atomic mass by 1, and the nucleus transforms into a different element. A common example is carbon-14 decaying into nitrogen-14. Gamma decay is the final type of radioactive decay we'll discuss. Unlike alpha and beta decay, gamma decay doesn't involve the emission of any particles. Instead, it's the release of energy in the form of high-energy photons, particles of light. These photons are created when the nucleus transitions from a higher energy state to a lower energy state. Think of it like a nucleus vibrating with energy, and then suddenly relaxing, releasing that energy as a gamma ray. Gamma rays are the most penetrating type of radiation, able to pass through dense materials like lead and concrete. They require significant shielding, often in the form of thick concrete barriers, to effectively absorb them. The emission of a gamma ray does not change the element itself. It simply reduces the nucleus's energy. It's important to note that these three types of decay, alpha, beta, and gamma, frequently occur in combination within a single radioactive atom. A nucleus might undergo alpha decay, immediately followed by beta decay, and then finally emit gamma radiation. The specific pattern of decay for any given radioactive element is determined by its half-life, the time it takes for half of the atoms in a sample to undergo decay. The half-life varies dramatically, ranging from fractions of a second to billions of years. In a nuclear power plant, the fuel rods containing uranium-235 are constantly undergoing radioactive decay. This decay is the source of the heat that drives the steam turbines, generating electricity. The power plant's design incorporates sophisticated shielding and containment systems to prevent the escape of these radioactive particles and photons. These systems are crucial for ensuring the safe operation of the plant, minimizing any potential exposure to radiation. Careful monitoring and regulation are in place to account for the ongoing, natural process of radioactive decay. The controlled release of energy from this decay is what makes nuclear power a viable source of electricity, but it always demands respect and meticulous attention to safety protocols. The journey of a nuclear reaction isn't a straightforward one, like a simple spark. It's a delicate dance of particles, a carefully orchestrated event demanding precision to prevent a runaway cascade. Early designs for nuclear reactors, those that paved the way for the immense power we now associate with nuclear energy, relied on a clever material called graphite to help control this dance. Graphite, a form of carbon, isn't flashy or glowing itself when exposed to the energy produced, but it played a surprisingly vital role in the initial development of reactors, notably the design championed by Enrico Fermi and his team at the University of Chicago in 1942. These pioneers were seeking a way to rapidly produce neutrons, the tiny, subatomic particles that are the heart of a nuclear reaction. Neutrons, when colliding with the nucleus of a uranium atom, could trigger further fission, a splitting process that releases enormous amounts of energy. However, the neutrons produced in this initial fission were traveling incredibly fast, and they were bouncing off the uranium fuel rods themselves, scattering in random directions. This meant many of these energetic neutrons wouldn't actually collide with uranium nuclei, resulting in a wasteful and inefficient reaction. Enter graphite. Graphite, unlike the dense uranium, is a light, porous material. It's essentially a layered structure made of carbon atoms arranged in hexagonal sheets, like stacks of paper. This structure is remarkably good at absorbing some of the kinetic energy of those newly created high-speed neutrons. When a fast neutron slams into a graphite atom, the graphite atom absorbs much of the neutron's energy, slowing the neutron down considerably. This slowed-down neutron is far more likely to then collide with a uranium nucleus, initiating further fission. It's like trying to hit a moving target. A fast-moving ball is difficult to hit, while a slower one is much easier. Graphite acted as a brake for the neutrons, reducing their speed and increasing the probability of a successful collision. The graphite moderator, as it was called, wasn't actively changing the neutrons themselves. It was simply reducing their momentum. The graphite structure provided a multitude of surfaces for these energetic neutrons to interact with, effectively diluting their speed and directing them towards the uranium fuel. The specific type of graphite used in these early reactors was a particularly pure form, often referred to as Pittsburgh graphite. This graphite was carefully processed to remove any impurities that might absorb or scatter neutrons, further maximizing its effectiveness as a moderator. The amount of graphite used in a reactor core was precisely calculated. Typically, it constituted a significant portion of the core's volume, often around 30–40%, depending on the reactor design. The design of the reactor core itself was crucial. In these older reactor configurations, such as the Chicago Pile 1, the graphite moderator wasn't uniformly distributed. Instead, it was arranged in a layered fashion, with alternating layers of graphite and uranium fuel rods. This layering further enhanced the moderation process, creating a series of zones where neutrons would slow down before encountering a uranium nucleus. The arrangement was carefully controlled to ensure that the reaction chain continued at a manageable rate. If the neutrons were allowed to simply scatter without moderation, the reaction would quickly become uncontrolled, leading to a dangerous and explosive situation. The graphite, therefore, wasn't just a passive component. It was an active participant in regulating the reaction. Furthermore, the graphite wasn't just used for slowing neutrons. It also helped to reflect some of the neutrons back into the core, creating a closed loop where neutrons could repeatedly collide with uranium nuclei, sustaining the chain reaction. This was particularly important in the early designs, which lacked sophisticated control mechanisms found in later reactor generations. The success of the Chicago Pile 1 demonstrated the fundamental principle. A moderator could reliably control the rate of a nuclear chain reaction. This achievement revolutionized the field and set the stage for the development of larger, more powerful nuclear reactors. It's important to recognize that the role of graphite evolved considerably over time. Later reactor designs, particularly those utilizing enriched uranium and advanced control systems, relied less on graphite for moderation and more on water, either light or heavy, to achieve the same effect, alongside more sophisticated methods of controlling the reaction rate. However, the foundational principle established by Fermi and his team, using graphite to tame the energy of neutrons, remains a cornerstone of nuclear reactor design, a testament to clever material science and a deep understanding of physics. The heat generated within a nuclear reactor doesn't simply vanish after producing electricity. It's a truly remarkable transformation, and the aftermath of this process presents a fascinating and somewhat complex challenge for energy producers. After roughly 10 to 15 years of operation, the fuel rods within a reactor core become what we call spent fuel. These rods are no longer optimally suited for generating electricity. They've become intensely radioactive, not just because of the uranium that initially fueled the reaction, but because of the creation of new, highly energetic elements during the fission process. This spent fuel is incredibly dense with radioactivity, requiring careful management to prevent harm to people and the environment. The immediate volume of spent fuel generated is considerable. A typical nuclear power plant produces around 20 metric tons of spent fuel per year. Now, this fuel doesn't just sit there. The fission process itself has produced a variety of radioactive isotopes, many with incredibly long half-lives, meaning they take hundreds of thousands, even millions of years to decay significantly. These isotopes include plutonium-239, americium-241, and strontium-90, alongside the original uranium and plutonium. The sheer quantity of these radioactive materials necessitates robust storage solutions. Initially, most spent fuel is stored on-site at the nuclear power plant itself. This typically involves placing the fuel assemblies in massive, shielded pools filled with water. The water serves a dual purpose. It provides cooling, absorbing the heat generated by the residual radioactivity, and it acts as a radiation shield, absorbing much of the intense gamma rays emitted by the fuel. These pools are designed with multiple safety systems, including backup power sources and containment structures, to ensure the safe containment of any potential release. However, these pools are not a permanent solution. The volume of spent fuel steadily increases as new fuel is generated. The long-term storage strategy has largely revolved around dry storage casks. These are robust, steel and concrete containers designed to passively contain the spent fuel for extended periods. The casks are designed to withstand extreme conditions, earthquakes, fire, even impacts. They rely on the natural insulating properties of the materials surrounding the fuel assemblies to maintain a stable temperature and minimize the release of radiation. These casks are often placed in specially constructed facilities, often located near the power plants, for added security and ease of management. But the question of what to do with this fuel becomes even more pressing when considering the potential for further utilization. Some nations have explored, and some are actively pursuing, reprocessing technologies. Reprocessing involves chemically separating the uranium and plutonium from the spent fuel. This isn't about creating a new fuel rod in the same way as initially fueling a reactor. Instead, the recovered uranium can be converted back into uranium oxide, which can then be used as fuel in conventional reactors, a process sometimes referred to as breeder reactors, though this is a more complex operation. The plutonium recovered during reprocessing can be fabricated into fuel for specialized reactors that utilize a plutonium-based fuel cycle. The reprocessing of spent fuel is a highly complex and controversial undertaking. It presents significant technical challenges, particularly regarding the handling and management of the radioactive materials involved. Furthermore, there are serious concerns about the potential for weapons proliferation. Separating plutonium, a key ingredient in nuclear weapons, from spent fuel creates a pathway that could be exploited. Strict international safeguards are essential to prevent this misuse. There are different reprocessing methods, each with its own advantages and disadvantages. Some techniques like the PUREX process, plutonium-uranium recovery extraction, are widely used. It involves dissolving the spent fuel in nitric acid and then separating the uranium and plutonium using solvent extraction. Others, still under development, aim for more complete separation, potentially recovering a wider range of valuable elements. The debate surrounding spent fuel management is multifaceted, encompassing economic, environmental, and security considerations. The most immediate solution, continued on-site storage, is costly and requires significant land area. Reprocessing offers a potential pathway to reduce the volume of waste and recover valuable resources, but it comes with inherent risks and complexities. The future of spent fuel management likely involves a combination of strategies, incorporating advanced storage technologies alongside carefully controlled reprocessing, all underpinned by stringent international regulations and safeguards. Ultimately, it represents a profound challenge in harnessing the power of the atom while mitigating its inherent risks. Research continues into alternative fuel cycles, focusing on designs that minimize waste generation. Some concepts involve using the entire fuel assembly as fuel in a highly controlled manner, reducing the amount of plutonium produced. Others explore the possibility of transmutation, where radioactive elements are converted into stable ones through nuclear reactions. a process that is still largely theoretical but holds immense potential. The goal remains the same: to manage the legacy of nuclear energy responsibly, ensuring the safety of future generations and securing a sustainable energy future. It's a continuous process of learning, adaptation, and refinement, driven by scientific innovation and a commitment to safety. The world of nuclear energy has always been built around a fundamental reaction: the splitting of atoms, specifically uranium, to release tremendous amounts of heat. Traditional nuclear reactors, those that have dominated the energy landscape for decades, use a process called thermal fission. These reactors rely on a moderator, substances like graphite or water, to slow down the neutrons released during fission. These slowed neutrons are much more likely to cause further fission events, sustaining the chain reaction. However, this approach presents some inherent limitations, primarily related to the long-term utilization of the fuel itself. The slowed neutrons, while efficient at producing heat, don't always lend themselves to the most efficient extraction of energy from the uranium fuel. There's a natural tendency for some neutrons to escape the reactor core without participating in further fission, representing a loss of potential energy. Now consider a different possibility: a path that promises a more complete and arguably more elegant solution: fast neutron reactors. These reactors operate on entirely different principles, exploiting a phenomenon known as fast, or high-energy neutrons. Instead of relying on a moderator to slow them down, fast neutron reactors are designed to utilize neutrons that are already traveling at incredibly high speeds, almost the speed of light. This seemingly small change has significant consequences for the reactor's performance and the way it interacts with the fuel. The core of a fast reactor is typically constructed from materials like zirconium alloys, which are exceptionally resistant to the intense radiation environment. Within this core, the fuel is usually uranium-238, the most abundant isotope of uranium. Unlike the thermal reactors that primarily rely on uranium-235, uranium-238 itself can undergo fission when struck by a fast neutron. This is a crucial difference. While uranium-235 is the easy-to-split isotope, uranium-238 requires a higher energy neutron to cause fission. Fast neutrons provide precisely that. This ability of uranium-238 to fission with fast neutrons dramatically increases the overall energy yield from a single uranium fuel rod. Think of it like this: in a thermal reactor, you're getting most of the energy from a carefully selected, easily split piece of uranium. In a fast reactor, you're harnessing the potential of all the uranium, including the harder-to-activate isotope. The conversion ratio, the amount of energy you can extract from a given amount of uranium, is significantly higher in a fast reactor. This translates directly to a more compact and efficient power plant. Furthermore, the operation of a fast reactor creates a self-generating epithermal, or thermal neutron population. As fast neutrons collide with the uranium-238, they slow down, becoming thermal neutrons. These thermal neutrons then go on to induce fission in the uranium-235, creating a continuous cycle of energy production. This self-sustaining thermal neutron population is a key factor in the operational stability of fast reactors. One of the most remarkable aspects of fast reactors is their potential for breeder operation. Traditional reactors consume uranium, they use it up. A breeder reactor, however, actively creates more fissile material, primarily plutonium-239 from uranium-238. This process is achieved through a phenomenon called transmutation. Essentially, the high-energy neutrons bombard the uranium-238, transforming it into plutonium. This newly created plutonium then becomes the fuel for further reactions, sustaining the chain reaction. The production of plutonium is a crucial element of the breeder concept. It allows a relatively small amount of uranium to generate a much larger supply of plutonium, effectively extending the lifespan of uranium resources. The breeder concept addresses the long-term sustainability of nuclear power, particularly as readily available uranium supplies dwindle. The spent fuel from a breeder reactor, while still containing plutonium, is significantly different from the spent fuel produced by thermal reactors. It's often viewed as a valuable resource rather than a waste product. The implications for fuel management are profound. Rather than storing vast quantities of highly radioactive spent fuel, which remains hazardous for thousands of years, a breeder reactor could convert this fuel into a more manageable form, a fuel that can then be used in other advanced reactor designs, potentially even in smaller, more flexible power plants. Concepts like actinide burning also become viable. Fast reactors can effectively burn, that is, fission, the longer-lived, highly radioactive transuranic elements like americium and curium that also accumulate in spent fuel. This reduces the long-term volume and radiotoxicity of nuclear waste. However, operating fast reactors presents unique engineering challenges. The high-energy neutrons create a significantly more intense radiation environment compared to thermal reactors, requiring more robust materials and stringent safety protocols. The rapid changes in neutron population also demand sophisticated control systems. Despite these challenges, ongoing research and development efforts are focused on addressing these hurdles, particularly in the design of advanced fast reactor concepts like molten salt reactors and lead-cooled fast reactors. These innovative designs aim to further enhance safety, efficiency, and waste management capabilities. The future of nuclear energy might well hinge on the successful development and deployment of fast neutron reactors. They represent a pathway to greater resource utilization, reduced waste, and a more sustainable energy future. While the journey towards widespread adoption will require continued innovation and careful consideration, the potential benefits of harnessing the full power of uranium and the surrounding elements are undeniably compelling. The ability to unlock the latent energy within uranium-238 offers a powerful tool in our quest for clean and reliable energy sources. The world of nuclear energy, as we've explored, has a rich and complex history. For decades, The idea of harnessing the atom's power centered around enormous, centralized nuclear power plants. These reactors, built on massive scales, produced vast amounts of electricity, but they also presented significant challenges related to cost, construction time, and the sheer volume of materials involved. As the world looked towards a future increasingly concerned with sustainability and diverse energy sources, scientists and engineers began to contemplate a shift, a move towards smaller, more flexible, and crucially, safer nuclear systems. This shift is largely spearheaded by small modular reactors, SMRs, and a wave of genuinely innovative reactor designs. SMRs, as the name suggests, are considerably smaller than traditional reactors. They're designed to be built in factories, often in modules that can be easily transported and assembled on site. This modular approach dramatically reduces construction time and cost. Think of it like building with Lego bricks, a smaller, more manageable project. These modules typically range from 30 megawatts to several hundred megawatts of power, a far cry from the multi-gigawatt capacity of large reactors. The key technological advancement driving SMRs is the use of advanced fuel designs and inherent safety features. Many SMR designs incorporate passive safety systems. These systems rely on established physical principles, gravity, natural convection, and diffusion, to shut down the reactor in an emergency, without the need for external power or human intervention. This is a crucial difference, increasing resilience against natural disasters or other unforeseen events. Several companies are currently developing SMRs, each employing slightly different technologies. Some designs utilize water as a coolant, similar to traditional reactors, but with enhanced safety mechanisms. Others explore the use of molten salt as a coolant, offering advantages in terms of heat transfer and the potential for direct use of the heat for electricity generation or industrial applications. Molten salt reactors, for instance, can operate at higher temperatures, leading to greater efficiency and the possibility of utilizing a larger fraction of the heat energy contained within the fuel. Furthermore, some SMR concepts are designed to utilize existing nuclear waste as fuel, effectively closing the loop and reducing the long-term burden of radioactive materials. Beyond SMRs, the future of nuclear power isn't just about scaling down existing designs. A fascinating collection of advanced reactor concepts are pushing the boundaries of what's possible. One particularly promising area is fast neutron reactors, FNRs, which we briefly touched upon in a previous part. However, newer FNR designs are moving beyond simply accelerating neutrons. They're actively incorporating them into the fuel itself. This allows these reactors to burn up a wider range of nuclear materials, including the troublesome transuranic elements, plutonium and minor actinides, that accumulate in spent fuel from existing reactors. This actinide burning capability significantly reduces the long-term radioactivity and volume of waste produced. Another area of intense research is the development of traveling wave reactors, TWRs. These designs rely on the concept of a wave of nuclear reactions propagating through the fuel. The fuel pellets are arranged in a specific geometry, and the neutrons created in fission trigger a cascade of reactions, effectively surfing a wave of energy. TWRs are incredibly efficient at utilizing the entire fuel supply and are predicted to generate minimal, long-lived radioactive waste. They offer a particularly elegant solution to the challenge of waste management. Furthermore, the idea of fusion energy continues to hold immense potential, though it remains a significant technological hurdle. Fusion reactors, unlike fission reactors, don't rely on nuclear reactions to generate heat. Instead, they harness the energy released when light atomic nuclei, such as hydrogen isotopes, are fused together. Scientists are making steady progress in achieving sustained fusion reactions, and if successful, fusion power could offer a virtually limitless source of clean energy, with no greenhouse gas emissions and significantly less radioactive waste than fission. The materials science involved in these advanced reactor concepts is also undergoing a revolution. Research is focusing on developing new materials, such as advanced steels and ceramics, that can withstand the extreme conditions within a reactor core, including high temperatures, intense radiation, and corrosive environments. These materials are critical for enhancing the safety, durability, and efficiency of next-generation reactors. Looking ahead, the role of nuclear power, particularly SMRs and these innovative designs, is becoming increasingly important in the global effort to decarbonize our energy systems. They represent a path towards a more sustainable and resilient energy future, one where nuclear energy can contribute reliably and safely to meet our growing energy demands. The journey is complex, demanding significant investment in research, development, and deployment, but the potential rewards a cleaner, more secure energy future are undeniably worth the effort. As the mysteries of nuclear power gently recede, let your mind settle into quiet reflection. The energy of the atoms has now relinquished its hold, and the world around you begins to soften. If you're still awake and enjoyed this exploration, please consider liking this video and subscribing to Ultimate Sleep Doctor. Together, we can soothe more wandering minds, one peaceful night at a time. Allow your thoughts to drift, calm and unhurried, until sleep finds you, a warm and welcome embrace.